Hello, my name is Isaac Campos, and I'm going to present you the work in automatic flow for precise and approximated synthesis, developed by me, Augusto Berndt, Brunno Abreu, Mateus Grellert, Jonata Carvalho, and Cristina Meinhardt. First, I'm going to talk about the introduction and motivations, then I'm going to explain the decision tree Boolean synthesis, the automatic flow, evaluation for approximated synthesis, and then the final remarks. The advance of technologies creates the need for more complex functions that can represent integrated circuits. This brings some limitations to logic minimization and causes some traditional tools like Espresso, for instance, to be restricted to circuits with less than 20 bits inputs. Also, there is a trend in the use of machine learning in the market, and this can be explored in the logic synthesis stage. Approximate computing can provide interesting results too, providing a reduction in power consumption when possible. Decision trees are a good alternative to optimize logic functions because tree-based methods are adequate for classification problems, which is the case of Boolean functions. Also, decision trees are convenient solutions since their outputs can be easily transformed into a sum of product or product of some function. And lastly, the algorithms for building decision trees are usually fast since they do not require expensive operations. These decision trees are formed by split nodes, which is a comparison between features and constants, and leaf nodes, that are the final outcomes of the model. Considering a Boolean problem, a feature is equivalent to an input bit, and the comparisons are simple checking on whether the bit is 0 or 1. Each output node is 0 or 1 as well. To exemplify how decision tree can be used to Boolean optimization, a full adder circuit will be used as a case study. The full adder is composed of 3 input bits and 2 outputs. The table of a full adder is presented in the left, as you can see, without the 8 minterms. In this example, only the sum output of the full adder will be used for logic optimization. The decision tree results from the training is shown on the image, and the expression is in the form of sum of products just below. As expected, the accuracy for the solution is 100%, since all the minterms contained in the validation file were considered also in the learning process. To demonstrate how to learn from an incomplete Boolean equation, we can assume a randomly defined incomplete truth table with half of the full adder's minterms. This reduces the table used to train a decision tree. The training set has then 4 minterms for training, and the other half of the complete table is used as the validation set. The learned expression and AIGs obtained had a reduction on the number of nodes and literals in the expression. However, as you can imagine, it will impact the accuracy of the solution, giving us approximate circuits. The goals of this work are to obtain logical optimization using decision trees, automate the logic synthesis steps, and consequently, as a result of the previous goals, obtain the reduction in the runtime of the logic synthesis for large circuits compared with some of the classic tools. Now I'm going to show you a comparison between the classic tool Espresso and our decision tree Boolean optimization. We used 90 benchmarks to run this comparison. First we ran Espresso for the 90 trained PLAs and then kept the results to compare at the end. Then we parse each PLA to decision tree inputs. That's because the tool we are using, C5.0, needs 3 different inputs to be able to run the learning process. With these inputs, we can generate the tree. Now, with the tree file ready, we have to convert it into EQN format. We need this format because the ABC tool, which is the tool we're gonna use to extract the informations about the circuit, only reads EQN formats. Not only EQN formats, but it doesn't read tree formats. So we need to make this conversion. And we chose EQN because it's very easy to transform a tree into a EQN file. And I'm gonna show you how easy it is right now. This is an example of a C5.0 tree output, and in this example we are going to transform this into a product of sums. So the first thing to do is to consider only rules that are from class 0. If we were making a sum of product file, we would consider class 1, but in this case we're going to make a product of sums. So this first rule is class 0, we're going to consider this rule. x3 equals 0, so we put in the equation the value x3. x4 equals 1, so we put in the equation the value not x4. And we just repeat this through the whole file. So x5, x6, x9. Now we can consider the other rules, like rule 2, which is also class 0. So x4 or x5 or x7 or x8 or not x9, because x9 equals 1 in rule 2. So this is the result of our conversion from a tree file into a EQN file. For the example that I just showed you, we used product of sums, but for this flow of comparison we used sum of products, which is very similar. And now we evaluate the final circuits with ABC, extracting the data needed to make this evaluation, which were nodes, number of nodes, and accuracy. To calculate these results, we made number of nodes over the accuracy result, which gave us 10.21 for espresso and 0.75 for C5.0. In this case, the lower the result, the better. And here are the average number of nodes and accuracy for espresso and C5.0, considering 90 benchmarks. But to be sure that this decision tree is a good alternative, we decided to compare other methods with it. So this workflow presents the methods that were compared with the decision tree approach and will be presented next. We call these three methods direct Verilog, which shows the simplest and most direct way to obtain the synthesis result, ABC optimization script, which goes through an optimization process in the traditional ABC logic synthesis tool, and the decision tree training for logic synthesis flow, which is the focus of this work and intends to achieve the goals mentioned previously. This decision tree flow is integrated with commercial FPGA and ASIC synthesis tools to show the impacts in terms of area and delay. The possibility to change the way the decision trees are built by modifying the tree generation parameters allows to control the trade-off between area, delay, and the circuit's output quality. This process ends after we obtain the area and timing results from the synthesis of the hardware description. Three tools were used to help in the automation process. ABC, which is a public domain system for logic synthesis based on end-inverter graphs, or AIGs. It was used to make conversions and optimizations, basically. C5.0, which is a decision tree implementation that takes the same name as the algorithm the software runs. Quartus, that is a software to design FPGAs used in the FPGA mapping process at the end of the flows. And Genus, which is a software used to make the ASIC synthesis. Those three flows were compared so we could understand the impact of the decision tree on the final result of the circuits. They all have some steps in common. One of them is the split outputs. The split outputs method was necessary because ABC does not accept PLAs with more than one output bit, at least in this ABC version we used. This method is then the first thing to run in this flow and also in the next ones to be presented, as you will see. This first flow seen on the screen was called direct Verilog synthesis because it basically reads the PLA files that represent the circuit's tables and converts it directly to Verilog. The tool used for the conversion was ABC, which already makes some optimization during this process. In addition, Quartus also optimizes during the mapping. The second method is the ABC optimization script. In this case, after reading the PLA, ABC converts the file to the AIG format in order to use the compressed 2RS optimization flow, which aims to rebalance the AIG and reduce the number of its nodes. After this optimization is done, it converts the AIG to a Verilog file that will be synthesized by Quartus as in the previous example. The last approach is decision tree training for logic synthesis flow. Here, after we got the tree file after the learning process, this tree is transformed into a sum of products, as showed previously, and this EQN file is then read by ABC and converted into AIG, and then Verilog. But we need this AIG intermediate format because some of the values of the results that we have to extract for the final comparison are made at this format. So if we didn't need these results for comparison, we could convert the EQN to Verilog directly, not being necessary to go through this intermediate format AIG. Here are some of the FPGA and ASIC synthesis features used in this workflow. We used two benchmarks to be run by the methods. Both of them are composed of complete truth tables, but the decision tree synthesis can provide an approximate computing logic as demonstrated by our analysis. After splitting the outputs to run the synthesis flow, they can present different accuracy results. The accuracy of the analyzed benchmarks outputs can be seen on the right. The decision tree accuracy is 100% for most outputs on the ALU4 circuit, despite two outputs that are limited to 98.1 and 99.3%. The decision tree accuracy for the PDC circuit presents only one output with less than 99% of accuracy, and the majority of the 40 outputs reaches over 99.5%. The impact of this loss in accuracy is highly dependable on the application. Here we can notice more specifically the results. We have the benchmarks ALU4 in yellow here and PDC in blue, and the three methods: decision tree, ABC optimization script, and direct Verilog. For the ALU4 benchmark, we had a very close area to the other two methods, and also the total power was very close to both of the methods, to the other two methods. But for PDC, we had a considerable reduction in the area, and also a considerable reduction on the total power. So in the previous image we saw the ASIC synthesis results, and now the FPGA synthesis. And in this FPGA synthesis we were not able to get the power consumption, but we were able to calculate the area and delay. So here the area is calculated by the number of lookup tables of the FPGA board, right? So 275 versus 624 and 588 resource or lookup tables for ALU4, and 26 against 108 and 111 for the other methods for the PDC benchmark. So a very considerable shrunk in both areas. And in the delay results, we can notice that it got very close, very similar to the other methods in both cases, ALU4 and PDC. So concluding, this work evaluates the impact of adopting a decision tree logic synthesis flow to reduce circuit power, area, and delay. The test environment adopts the FPGA and ASIC synthesis as a case study and uses the ABC optimization script as baseline. The current decision tree flow can be explored to generate more power-efficient solutions at the cost of a tolerable level of accuracy depending on the application scenario at hand. And indeed, this can be an interesting and fast approach to application designs applying approximate computing. Thank you for your attention.